I'm Pat Dugas. This screencast is about the remainder and factor theorems, which are two more tools we have in the toolbox of being able to determine the solutions or zeros of polynomials. So let's look at some terms. Synthetic substitution is a method of finding what a function's value is at a given point using synthetic division. A depressed polynomial is the result, part of the result of that synthetic substitution or the synthetic division. It is a simpler polynomial that results from dividing a larger polynomial by a factor, and it is going to be 1 degree smaller than the original as a result. So let's look at the remainder theorem. So if we take any polynomial, let's call it p of x, and we divide it by x minus r, what we have left is a constant. And it turns out that constant is actually the value of the original function evaluated at that r value. And that's a useful idea, particularly when it's 0, as we'll look at in the factor theorem. In equation form, the dividend p of x, the polynomial we're looking at, is equal to the quotient, what's the result of the division, times the divisor itself, the x minus r, plus some remainder. And as it turns out, that remainder is actually the value of the function at r, where r is the factor. So looking at an example, let's say we have x squared plus 6x plus 2, and we divide that by x minus 4. The result through synthetic division is going to be x plus 10 plus a remainder of 42 divided by x minus 4. And so here I've divided this polynomial, x squared plus 6x plus 2, and of course that's a separate screencast on synthetic division. But when I use the synthetic division, I get x plus 10, which is these two terms here, plus a remainder of 42. Now what the remainder theorem tells us is that f of 4, this function evaluated at 4, is going to equal 42. I know that because that's what's left over. That's the remainder. And indeed, you can check that out by direct substitution as well. If I took a 4 and put it into the original function, x squared plus 6x plus 2, I get 4 squared plus 6 times 4 plus 2, which is 42. So it checks out. Let's look at an example of using synthetic substitution to evaluate a function. So let's take a more complicated function than that. 2x to the fourth minus 5x squared plus 8x minus 7. And we want to find f of 6. Now, certainly we can do direct substitution of 6 in for x and find the answer. But we can also use synthetic substitution. So what we're going to do is set up a synthetic division of this polynomial, and then using x minus 6 or using an r value of 6. And if r equals 6, whatever we get as our remainder from this division, 2x to the fourth minus 5x squared plus 8x minus 7 divided by x minus 6. The remainder of that is going to be f of 6. So if we do that and we put all the coefficients. Now very important, if we have a term that's missing, a degree that's missing from our original polynomial, we need to put in a 0 for there. And since there is no x to the third term, we got to put a 0 in the x to the third spot. So that's why we have 2, 0, negative 5, 8, negative 7. When we do the synthetic division, this is the result. And 2,453 is the remainder. So what I know is that f of 6 is equal to 2,453 by the remainder theorem. Now what's left over also as a polynomial is called the depressed polynomial. If you want to factor it further, you look at that part, and we're going to do that here in a second. So the factor theorem is a special version of the remainder theorem. When the remainder is 0, then that must mean that x minus r is a factor, which it holds true for integers as well. For example, if I have 24 divided by 3, that's equal to 8 with a remainder of 0. That tells me that 3 is a factor of 24. It's a similar idea for polynomials. So the remainder of x minus r using synthetic substitution is equal to f of r. If that f of r is 0, then that tells us that x minus r is a factor of the polynomial. That means there's nothing left over. It is a perfect factor. That turns out to be a useful application of the factor theorem and the remainder theorem. So let's verify to see if x minus 3 is a factor of x to the third plus 4x squared minus 15x minus 18. Now it should be noted there are other ways to factor this as well, which we talk about in other screencasts. So if x minus 3 is a factor, we should get a remainder of 0, and then we'll, by the factor theorem, and then we're going to continue to factor the depressed polynomials until we get all the factors. Now we know from other means that since it's a third degree polynomial, there are as many as 3 roots to it. And so let's set up, we have 1x to the third, 4x squared minus 15x minus 18. We're dividing that by x minus 3. We're using the synthetic division, separate screencast. Remainder is 0. Bing, bing, x minus 3 is a factor. So now what we're going to do is we're going to take the depressed polynomial, which is this right here. And that turns out to be x squared plus 7x plus 6. And so factoring out this polynomial at this point looks like this. X minus 3 is a factor, and so is x squared plus 7x plus 6, because that's what's left after a remainder of 0. But we can use other techniques, namely the x technique, to factor out x squared plus 7x plus 6. Well, we know that they have to multiply to give us 6, the factors, and they have to add to give us 7. Well, that's positive 6 and positive 1. So we'd write x minus 3 times x plus 6 times x minus 1 equals 0, which means we have 3 factors. We have found our 3 factors. 3, using the zero product property, negative 6, and negative 1. So we know that those 3 numbers are the 3 factors of the original polynomial. We looked at the remainder and factor theorems. Using synthetic substitution, we can not only evaluate a function based on the remainder of that synthetic division, but if it's 0, we can use the factor theorem to determine that that is a factor of the function, and then use other tools to continue to factor.